Okay, great. Thank you very much. Yeah, thank you for giving me the chance to speak and putting on this fantastic workshop. As someone new to the field, I really appreciate all of the talks, everything I've learned, especially if you're doing introductory material. It's helped at least one person, so thank you. Also, it's the last talk of the day. If you want to stand up and stretch, I highly encourage it. I won't be offended. You want to run around in the back, that's cool. Just listen while you are. So I'm Tom Esposito. I'm a researcher at the SETI Institute in California and UC Berkeley as well. And I am the science team manager for Unistellar, telescope maker, telescope company based in Marseille, France. And I want to tell you about the Unistellar network and what we're doing with this group of citizen scientists to follow up transients as quickly as possible. So just briefly on the Unistellar network overall, we have 5 main science campaigns that we run. And this is all led by astronomers at the SETI Institute. We do asteroid occultations, planetary defense for near-Earth asteroids, exoplanet transits, especially following up NASA TESS planet candidates, which is something I used to lead, cometary activity, and then what I'll talk about today, the Transient Events Program, which we've nicknamed Cosmic Cataclysms for a little bit more flair. I won't talk about those others, but if you're interested, please let me know. Go. Okay, this is just briefly our team. We have 5 astronomers who are leading the science programs, myself included. And then we have Ian, who's an education specialist leading that our education programs more generally. And then Amaury here has been working with me for the last month or so on building out our transients program. He's a French student who's in San Francisco for about a year or so. And we're a little bit spread out across the US at times. We've built a few scientific partnerships as part of these programs. AAVSO is up there, initially with the Exoplanet Transits program. Now we're starting to work with them on transients and maybe variable stars. We have a bunch of others, and now I'm happy to add Astro-COLIBRI up there as well. And this partnership between SETI Institute and Unistellar was formalized in 2019 as part of this memorandum of understanding where Unistellar says, hey, we want science to be part of our company and part of what we're doing with our telescopes. Can we have SETI Institute astronomers design and curate and lead these programs to get people involved and to actually use the data that we can get from these telescopes? And I'll talk more about what the telescopes actually are in a minute. But first, to just give you a picture of what we want to do with the transients program. And really, we think that our strength is in being fast, having a fast response to newly discovered candidates, and also a little bit on our broad geographic coverage, which I'll talk about. So goals, we want to routinely be getting photometry, optical broadband photometry, in under an hour for whatever candidates that are suitable to us. And we think best case scenario with the way that our alert system is set up, which I'll go over, we can get our first data in less than 5 minutes. We want to also coordinate longer term monitoring and follow-up of these targets. I'll show we have an example of one target we've been following for 6 months. And that's just a matter of how many telescopes we have to do the observations well, the attention span of our citizen scientists who are often quite into it. And then with Vera Rubin and LSST coming online in mid-2025, fingers crossed, we hope to be part of that entire discovery process where LSST may be discovering entirely new phenomena or learning new things about existing phenomena, and we want to be part of that. So just a timeline is we started, the Unistellar network itself was formed in early 2020. We've been running the transients program since June of last year, but it really was in beta mode until February of this year. That's when our alert system came online that I'll describe. And just in August, we added our Astro-COLIBRI notifications, which is adding an important component to what we're doing. So this is the main instrument that we're using in this network of telescopes. It is the Unistellar Enhanced Vision Telescope, or EV scope. It's small. It's probably the smallest telescope that's been talked about in this workshop, I think, with the exception of there's a 50 millimeter or something that was mentioned earlier. It's an 11 centimeter aperture. It has a camera and a computer built in, and the camera has a CMOS RGB sensor. It's actually sensitive from 400 to more like 950 nanometers, so we leak into the infrared. It's very autonomous. It's really easy to use. Was hoping to do a demo after this talk, but I don't think the clouds are going to allow it. I'm happy to talk more about how the telescope works afterwards. Importantly, so there's two different models that are available right now, and these are their specs. It's roughly a ½ degree by ½ degree field of view, or a little bit bigger, and a relatively small pixel scale, small enough for what we need to do. And kind of one key thing for the citizen science aspect is when people record their data, it's really easily uploaded to us over Wi-Fi. They just tap a button in the app, which controls the entire thing. And so I like to say that people come to the Unistellar network for the enhanced vision, but they stay for the science. And so the enhanced vision is really the core feature of the EV scope. It's a combination of the hardware and the software to give you real-time deep sky views, even from really bright places like cities, so that you can see things like the Eagle Nebula and galaxies and comets, which look even better than this without the lights on in this projector. I can show you other examples as well. And so people are attracted to that, especially folks who don't think or don't know yet that they're interested in astronomy as a science. But then we offer all of them access to our science campaigns, and then we get them involved and they get deeper into what astronomy is. They learn more about science as a process and keep using the telescope more than just once every year to look at a nebula. So this is the network as of 2019, end of, or maybe early, yeah, end of 2020, where each of the telescopes had been used at that point. And if I play this, this is how it's grown until 2023. So you'll see high concentration in Europe and the United States and Japan. That's where our distribution started out. We've been adding telescopes in other places around the world since then, and especially in the Southern Hemisphere. We have a pretty strong presence in New Zealand and Australia already, but we're really trying to distribute more and encourage more citizen scientists in South America and Africa. We've had over 500 people, so there's over 10,000 telescopes around the world right now. Not everyone is doing citizen science. It's to be expected. Totally cool. We've had over 500 people actually contribute data to our science campaigns. So that is, what, 5%? Did I do the math right? No, yeah, that's right. 5%. We want to get that up to 25%. We have some various strategies. We're going to try to do that. And then we have over 1,200 people in our Slack workspace, which is how we mainly communicate with our citizen scientists. Anyone can join that for free. They're specifically following the Transients program, so we think at least that they're interested. They're more like potential observers we could add soon. And then we have even more than that in our Slack workspace in general, following the other science campaigns, et cetera, who we have a direct line to those people. So this is it currently. Okay, so how do we get people into the citizen science programs? We try to make it as easy as possible. So this is how we encourage participation, how we get as much data as we can. We have all of our target information, for example, is posted on a web page that anyone can see. It's public. We have our Slack workspace where we post alerts to a channel specifically for alerts that people can subscribe to. And then we have the Astro-COLIBRI app, of course, which people can get real-time notifications on their phone. And then all of the telescope operation and all of the taking of science data happens in the mobile app from Unistellar. That has a dedicated mode just for this. And then we send results of people's observations. What did they see? What did we learn from it? We send those back on our Slack workspace automatically, usually, within about 24 hours of when they take and upload their data. So this is with our automatic pipeline that's running in the background all the time. And so that's an example of what one of the reports looks like for Supernova 2023 IXF in M101. Okay, so how does the alert system that we built work to get from a candidate that's been identified? And for now, we're focusing on supernova candidates and other novae type things from ZTF. That was where we started, and we're adding components soon. How do we go from there to actually collecting data? So there's a server running on AWS in the cloud that checks for new alerts every 1 minute from the LRC broker. And I am looking at adding other brokers. I have looked at Think and probably will incorporate that soon. We then filter those alerts even further to make sure that they are suitable for our telescopes. It's a tiny telescope. It can't go down to 20th magnitude, for example. We're not going to try to observe those. For example, especially we make sure that they have a reasonably high probability of being a real supernova based on the LRC classification system, and that there's no bright sources nearby. There tends to be a lot of false alarms, or a significant number of false alarms from bright sources. We're filtering them out as well. So that's always running in the background. This is kind of like a log that you don't have to read of what it looks like. From there, as soon as an alert is selected, within about 30 seconds, we send everything to our webpage, the Slack channel, the Colibri app. Those are examples of what those look like. And then people can basically click on, in the Slack post, you can see there's a deep link to observe link. There's also a deep link in the Astro-COLIBRI event details. And this deep link, you tap it from your phone and it opens the Unistellar app and pre-fills everything that someone needs to do in observation. So RA and DEC coordinates to point the telescope, and then all the camera settings, exposure time, gain, duration of the observation. So it's basically from when someone sees that the target exists, it's 3 taps on their phone and they're taking data. And so really that all happens within 2 minutes of when the alert is identified, and which means that's where I kind of get the idea that you can get on source and taking data within 5 minutes or less. We've been adding multi-messenger alerts, so gravitational waves, GRBs, and neutrino sources. This is we're working with Sarah and the Grandma Kilonova Catcher team. We again do more filtering. We plan out and prioritize fields of view to do the localization of poorly localized targets like gravitational wave sources. I'm probably going to replace this with something like TilePi now that I know it exists. Another useful thing I've learned this week. And then we do the same process where we send that alert out to our observers, and we have to develop some sort of new tool here to get some feedback on what fields of people have observed, so we don't duplicate observations too heavily, things like that. We may use some of the other features I've learned about already here as well for that. And this is work by Amaury Parachot, that French researcher who's with us for the summer, not for the summer, for about the year. Okay. So now just some examples of results and the data and the science that we've gotten from this program. First is Supernova 2023 IXF. So this is well known at this point, the M101 supernova from May. This was one of our first tests of the program when it was fully running. Unfortunately, the alerts missed it. The broker did not identify this as a supernova, kind of strangely, but it didn't. So we didn't catch it with our automatic alert system. I added it manually. We got data still pretty quickly within our first real science observations were within about 2 days after the alert, the initial discovery. But there are so many people in this Unistellar network who are observing every night. M101 is a popular target. We had serendipitous observations of this supernova going all the way back to days before the eruption actually happened. So when we took all of those data, with the observer's permission, of course. We actually ended up with our first detection was less than 5 hours after the earliest detection by any telescope. And then we have non-detections well before that. And yeah, we go all the way back to 16 hours before the initial discovery epoch. So we have a pretty well sampled early light curve here. And that's even despite not getting the alert automatically, which is kind of out of our control without adding other brokers. Pretty dense sampling. Every 3.3 hours or so on average, we got a measurement. And this was just the first 35 days of the light curve that we published in a AAS research note pretty quickly with just measuring the peak magnitude and the peak time. What does it look like now? So this is our full light curve up until a few days ago. You can see we have a lot of measurements. Those are the colored points compared with ZTF. Our photometric calibration is a little weird because we have this, didn't mention it earlier, but the camera sensor has a Bayer matrix pattern. So we get red, green, and blue pixels in every 2x2 square pixels. And so when we combine that full band pass, sometimes converting to something like a V band is a little tricky. But we still capture the shape properly. And we've been, that 502 number is out of date, something like 560 measurements since May. And I think of the 160 or 170 possible nights since that supernova went off, we've observed all but 15 of them, at least once. Here's TCRB, which was mentioned earlier. We've been monitoring this since July. Actually, one of our citizen scientists is also a professional astronomer at Hofstra, Stephen Lawrence, who recommended, let's look at this and catch it when it goes off. And so we've been watching this target for variability. Occasionally we get a bad data point there. I should probably just trim that one out with a giant error bar. But we'll keep watching this until it goes off. The plan is to kind of, I'll add in a kind of internal feedback loop where as soon as we detect that our magnitude is rising, or our brightness is rising, we'll trigger a second alert and have people really focus on it. We also have to do things like adjust our exposure times and stuff because this is going to get very bright very fast. And it's the lack of data points on the right side there is not so much people losing interest, it's just this target went behind the sun and it's been hard to observe, but it's coming back soon. Okay, just a couple more here. This is another cataclysmic variable that actually did go off that we've been monitoring. And this here, I'm just showing, there isn't anything particularly interesting about this target other than this bump here, which is seen by both ZTF and our data, and also by AAVSO, just demonstrating that we have the precision here to detect structure like this in light curves, right? So we're not just getting magnitudes plus or minus a magnitude. We're kind of in the usually 1/10 of a magnitude or better precision, even for fainter targets. I don't think I said it yet, but we can go down to V of 17 right now with a single telescope in about 2 minutes of integration from a typical site. That of course varies as people are observing from different locations. Some are brighter, some are darker. We think that, as Sarah mentioned earlier, in longer integrations of 20, 30 minutes, we can get to 17.5. And I'm hoping that maybe with a little bit of ingenuity with our data processing, maybe we can get to 18, closer to 18 in best case scenarios. And I just threw this one at the last minute. This is a recent supernova 2023 WRK that we've caught on the rise. So this was, this one just missed our alert cutoff. So I set a 16.8 magnitude cutoff for our alert targets. This was 16.9 when LRC identified it. We just missed it, but the grandma team asked us to observe it. And so we've been building this light curve ever since. This is, again, a zoomed in example of what our report looks like when we send the information back to our observers. And of course, we have all the details on the back end, the actual measurements. For example, we measure our the magnitude. We stack our images. The longest single exposure the EV scope can take is 4 seconds. That's just electronics limited. So we typically stack those images up to 1 minute, and we make our magnitude measurement from that. We just take our target and compare it to reference stars in the field of view with known Gaia magnitudes, convert to a Gaia mag, and then I do some hand waving to get to a V mag. I think I'll probably just in the future just stick with Gaia G to avoid having to do that. But we average, kind of take the mean and the standard deviation of those multiple 1 minute measurements to get the number that we report here. One thing we could do that I haven't done yet is actually stack together all the data from all the telescopes that observe simultaneously. That might help us get a little deeper to do. All right, and I think that basically brings me to the end here. I don't know how I'm doing on time. How much do I have left? I can exit, so I can actually maybe show a bonus. But I'll go through the summary here quickly and then come back to it. So what have we been doing so far with the Unistellar network follow-up of transients? We have this real-time alert system running. Right now, it's focusing on ZTF. LSST is the goal. We have this 3 routes for alerts to reach our observers in this network of 10,000 telescopes plus. We have that website. We have the Slack workspace and the Astro-COLIBRI alerts. If you want to go check it out, the website is alerts.unistellaroptics.com. Yeah, we've taken over 1,600 observations. Those are individual data sets. So those are not just like images. That's actual full data sets, anywhere from 10 to 30 minutes each, just since January 1st of this year. That's from over 180 different people around the world. And that's in every region, every continent except Antarctica. Those results all get processed automatically on our back end, which runs on AWS. That's a Python pipeline that I've built with the help of some other people. It takes about 10 to 20 minutes to process a full data set from start to final measurements. We can speed that up just by throwing more processors at that. And then the 24 hours back to the observer is really just a matter of waiting for them to upload their data, which is one kind of logistical hurdle that we need to work on when it comes to gravitational wave source localization, for example. We need to figure out how do we get people to take their images and then get them to us immediately. I think we can do it, but it's a challenge. Shown some of the light curves, for example. We've had over something close to 60 alert candidates since we turned that system on in February. And I think all but 7 of them, we've gotten at least 1 observation. And all of those are within at least a day or 2. Some of them just end up being, I cancel them right away because they're clearly false alarms. And then we're adding things like the Grandma alert stream for gravitational waves, GRBs, neutrinos. I think we can catch the brightest of those GRBs, the afterglows, as long as we can do it fast enough. So this is why we want one of the reasons we want to focus on speed. We want to catch these optical counterparts when they're bright enough for us to see them with our little telescopes. We want to get our photometry into public databases. It's no good to anyone if we're just sitting on it. I realize this, and it's something I've been bad about. It's just a matter of automating how to send it to places like AAVSO, TNS, other things like that. And we're also working on multicolor photometry. So I mentioned we simultaneously get red, green, and blue information from our sensor. We haven't yet split that up into RGB filter measurements. But we have a student working on that now, and actually a second student who will be working on that soon. We know how to do it. It's just a matter of getting our calibration right. And I'm always looking for new things that we can do with this network. So we want to be useful to the scientific community in general. I think I know what we're good at, but I don't know everything it's useful for. And so I'm hoping if you have ideas, please let me know. And maybe we can incorporate your science into our network. Okay, if I still have like 2 minutes, I can just show, because we can't go outside and look with the EV scope tonight. I was just going to show examples of some of the things it can see. Is there any way I can turn these lights off? Is it this big button? Yeah, no, just 2 minutes. Stay awake for 2 minutes. So things like the Running Man Nebula. So these are observations with an EV scope. Again, it stacks images in real time. It does light pollution filtering. It does image alignment. So you can see things even from bright places like the Running Man Nebula here. And this is probably in something like anywhere from 30 to 45 minutes of watching your target, but you see it improve in real time. So within the first 4-second exposure, you see the nebula, and then within about 30 seconds, you see it really well. And then after a few minutes, it looks great, and you just keep seeing that improvement every 4 seconds as it adds a new image until you get to something like this. This is a single telescope looking for about 30 to 45 minutes, something like that. This is probably from a better than average site. This is kind of one of our gold standard images, but we could see from a place like here, you're going to see something like this very close. Just some other examples I'll go through. A galaxy that looks pretty good. There's a smaller edge-on galaxy, so even smaller objects, you can zoom in, for example, when you're actually seeing it on everything is seen through the mobile device that you're looking at. Some of the telescopes do have an eyepiece, which looks at a OLED screen inside of the telescope. So there's no direct optical light path to your eye, but you can zoom in. You can do all kinds of image scaling of the brightness and things like that in real time. The Pillars of Creation and the Eagle Nebula. This is one of my favorites. I can't believe we can see the Pillars of Creation with the telescope. That's 4.5 inches or 11 centimeters across. Just 2 more. The Helix Nebula. Nebulae look great. The colors are real. This is not post-processed or anything. This is what you see in real time from the telescope. I think this is the Sculptor Galaxy, maybe. Again, you can see all of the dust lanes and the spiral arms. And then one last one. I think this is the Tarantula Nebula, only from the south, I think. But again, just something that you're just not going to see with a standard telescope of that size, or even a telescope 10 times larger. You're going to have a hard time seeing this at all, never mind with such detail. So that's it. I'll stop there. I'll go back to my summary slide. And I'll take any questions that you might have. I'll turn the lights back on.